Hey guys, welcome back to experiment number 6 or week number 6. This week, our chemistry might be a little bit more appealing since we will get to work with some solutions that change color, so that could be fun. Um, but before we do so, let's just do some housekeeping items. Remember to submit your lab report um, before the start of next week, as well as that pre-lab quiz, so we won't have to worry about measuring or calculating anything, of course, from last week's lab before the start of this week's lab. And so just submit everything on time. And then our safety topic for the week are just gloves. I've talked about these before, and I've told you that gloves are pretty cheap. So anytime that you get any kind of chemical on them, whether it be acetone or, I mean, unless it's water and you're confident it's water, acetone, sodium hydroxide, acid, whatever it is, just go ahead and take them off and just exchange them for a new pair because they're not meant to be permanent protection. They're meant to be primary and temporary protection. It's just as it says here, temporary barrier. So just as soon as you get something on, your gloves, take them off and move on. Um, and then, of course, you can go through the some of the composition of these gloves. And of course, when you get to organic chemistry, this is going to be a lot more important because you will definitely have a lot more opportunity to, um, well, I guess, get your hands wet with chemistry with a lot of these chemicals. And a lot of these will actually burn through your gloves. So you need to immediately change them as soon as you expose your gloves to any chemical, acetone or methanol, phenol, whatever it is, because they just will start melting your gloves, and then of course you'll start to feel it. It kind of burns actually once it gets past your gloves, and then there's no point in wearing gloves at all. So, and then of course these chemicals highlighted in red will penetrate the skin, so then they will also carry whatever chemicals are within those solvents past your skin, and that's when you're in deep trouble. So keep that in mind. Um, as soon as you get some spill on them, go ahead and change them ASAP. And one thing I forgot to mention is don't wear them outside of lab. As soon as you step outside, take both gloves off. You never want to wear lab, even if they're clean, even if they're super clean, you don't wear them outside of the lab because we just have to assume that they're dirty. And if I see you with gloves on, I just assume that you were just working with chemicals and you're contaminating doorknobs and touching everything outside of the lab, and it's just not good chemical hygiene. So let's keep that in mind. This week we're going to be working with our burettes again, and we're going to be doing titrations. So titration is really just a method that allows us to pour a certain amount or a volume of liquid into a separate liquid based on, and it helps us determine concentrations kind of through a gravimetric analysis type method, but without weighing anything. It's more through determining concentrations and volumes. So in this case, a lot of these titrations will have a color change, which indicates a neutralization, and the one that's known is called a titrant. So our titrant will go into our burette, and that's the one that we know the concentration of to determine the concentration of the one or of the sample below in the Erlenmeyer flask. And I'll kind of flesh out some of those details. So in this lab, what we're really focused on is finding the amount or the concentration of thiosulfate. And so in this case, we have our burette, and then we have an unknown amount of thiosulfate in our Erlenmeyer flask. So we don't know the concentration of thiosulfate. So our job today or this week is to figure out that concentration of thiosulfate. So what we do know is that thiosulfate will react with iodate to generate tetradienate and in a redox reaction. And essentially what happens is that iodate gives thiosulfate those three oxygens. And so consequently, Sulfur is oxidized because it now has 6 oxygens instead of just 3. And then iodine is reduced from 3 oxygens to no oxygens. And so if you calculate the oxidation states, we see that iodine is reduced from a +5 to a -1. And remember, it's -2 times 3, that'd be -6, and we have a -1. So then iodine has to be +5, and so then this has to be +6, so we can have an overall charge, or sorry, -6, so we can have an overall charge of -1. And same thing for sulfur. Sulfur goes here from an oxidation state of +2 to 2.5, which is actually interesting. And same idea, you have -2 times 6, and then that gives us, of course, -12, and we have to have a charge of -2, so we have to have a plus of 10, and so then this side has to be +10. Oh, what's 10 divided by 4? 2.5. That's how we get a 2.5 there. And so remember, a good way to remember the which one's being oxidized and which one's being reduced, you might have talked about this several times, but just a reminder, Leo the Lion or oil rig. This is one that I always remembered. Oxidation is losing, reduction is gaining. Seems counterintuitive, but it certainly works. For example, reduction is gaining electrons. Iodine is reduced because it's gaining electrons. And how you know it's gaining electrons? Because it's gaining negative charges. So this is gaining -6, right? And so it's gaining a -6, or you can say plus -6. Again, seems counterintuitive, but it helps. So again, our purpose for this lab is to determine the concentration of thiosulfate. And we know that this works because we know how much iodate we will put in. And so when we react those two and generate tetrathionate, we will be able to work backwards and determine the concentration of thiosulfate. So in this case, we will have our endpoint for our titration will be obvious because we will go from a purple, reddish Erlenmeyer flask to a clear Erlenmeyer flask. And that's how we know our titration is finished. What you don't want to do is to keep going. Once you see clear, you don't want to keep going past that because we're going to use the volume of titrate used. And if you keep going past that, as soon as it's clear and you keep going past it, then you are obviously using up more titrant, which will completely throw off our calculations. So once you start to get closer, and I'll talk about this in the next slide, you want to slow down the drip to maybe a couple drips every 10 seconds. So you'll know you're at the endpoint based on the color. So yeah, as soon as we have this clear color, that means that we have no more iodate. And that's this initial reagent that we know, which is our titrant. Okay, so and I show you this because ultimately this scheme here shows us the number of moles that we get from of thiosulfate that we get from iodate. So we're reacting those two, and that's important for us to know because that's going to help us work backwards, and we need that number. So this is a 1:6 ratio, as you can see, and so we'll keep that in mind. 1:6 molar ratio. We'll keep that in mind for our calculations. But when I show you the 1:6 ratio in our calculations, I want you to see where it came from. Let me think if there's anything else to add. I think that should be it. And that's the most important thing there. So I'll come back to our titration again, but what I do want you to do is we will be working with pipettes, glass pipettes, longer pipettes with red bulbs, and you will need to do this so that you can use, so you can add a certain specific amount of thiosulfate into the Erlenmeyer flask. So before you do that, so that we know that we've added a consistent amount, practice with water. These things are kind of tedious to use, and so you may not get exactly 10 mils the first time. It's kind of hard. So encourage you to practice with water first before you actually use the pick up that certain amount of thiosulfate for your Erlenmeyer flask. Again, because otherwise you end up using too much titrant and you run out and you have to kind of restart the lab again. So especially if you run out of titrant before your two trials. And so then once you feel pretty competent with setting the meniscus, then go ahead and move on to the transfer of our unknown amount of thiosulfate. Da, 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 da. Oh, okay, so I realized I said that backwards. Your thiosulfate will be in the burette. Sorry, I just realized I said that backwards the whole time. Your thiosulfate's in the burette. The known concentration is in the beaker or in the Erlenmeyer flask. So, and this is obvious, of course, too, because you rinse your burette with your thiosulfate solution and you fill it up, and you don't know the concentration of that, but you do know the concentration of the iodate. So prepare your potassium iodate. And this is similar to what we've done. You weigh out a certain amount, use a molecular mass to convert grams to moles, and then, of course, and you'll know the concentration once you put it into 100 milliliters. And then so you mix that up a little bit, and then you pipette 10 milliliters of that solution into an Erlenmeyer flask, and that's what we were practicing for. And then, of course, you add 6 mils of hydrochloric acid. Be very careful with or sorry, 6 molar, 2 mils of 6 molar hydrochloric acid. Be very careful with this because it's very caustic. So be very careful with that. And that's when your solutions should turn red. And so at this point, our Erlenmeyer flask has 12 milliliters of red solution. And it's a known concentration of potassium iodate. Right? And that's the concentration that you calculate based on how much you measure out. So then you begin the titration by slowly adding thiosulfate from the burette. So the burette's up here, and then you start dripping the thiosulfate down. And what you start to see is a color change. Maybe it becomes yellow instead of orange, or sorry, red. And it says orange here. I don't remember seeing orange in the past, but you might see a little bit of orange with as you start to add more thiosulfate. But what I will say, continue titration until one of the thiosulfate. Yeah, is that you want to maybe start off slow to see how how fast opening the stopcock will drip the thiosulfate out. Once you feel pretty confident that you can control it well, maybe you can speed it up a little bit, but maybe don't go beyond 10 milliliters very fast, because what you'll see is that as soon as this turns clear, if you go past it, you're going to have to restart again because you won't know what concentration or what volume of thiosulfate you added. So you want to do this pretty slow after a couple of milliliters, because one drop will turn of the thiosulfate solution will turn the iodate solution colorless. And here's what I mean by that. When you start off, this is what it should look like. And about, I don't know, 10 milliliters, 20 milliliters in, you might get something like this, that Gatorade looking color. When you get to this point, that's how you know you're close, because obviously it looks diluted, but also the iodate is reacting. But it literally could take one drop to go from the left picture to the right picture here. So once you get to this point, slow it down, maybe 2 or 3 drops every 10 seconds. Swirl it at the same time, because it might just be, if you just swirl it once, you might see that it just needed time to react. And so once you start to get to this purple, go ahead and start swirling as you add more thiosulfate solution. Otherwise, yeah, from the very beginning, use a steady drop rate. Important step I missed. When your solution turns yellow, go ahead and add 2 drops of starch solution. That solution will be on the bench top. And again, that's also when you know you're close. So go slow. You just need 1 drop to turn it clear, and then record the volume. So yeah, at this point, when you get that clear solution, you're going to record the volume of thiosulfate used, because remember, your burette, I don't know, you'll start, fill it up to around here. We don't know how much we're going to use total, so I'd say fill it up as high as possible without any danger of spilling over. And you might use from here to here, all right? Because as it drips, it's going to just go down in volume. And if you used this much, this, let's say this was 100 mils and this says now 80 mils, then you use 20 mils, right? So record that number down to 2 decimal places. And that's going to become important with our calculations. And so you're going to do this twice because you should have enough. Let's say in this case you use 20 mils, you still have 80 mils left. You can use another 20 mils. And the second time will be easier because you can probably go a little bit faster early on, and then when you get to about halfway, you can start to slow it down because you know what to expect. So you'll do this whole thing twice. Pretty simple. You won't have to generate a new solution of thiosulfate, nor will you have to generate a new solution of the potassium iodate because you've already generated that before in a big beaker. You just need to take 10 mils and transfer it into a fresh, clean Erlenmeyer flask. And then, especially if you overshoot it, then you pass the point of the solution turning clear. Then, of course, you might need to do a third or a fourth if you have enough volume trial to do that. And of course, remember, this is aqueous waste, so make sure you put it in aqueous waste carboys, not down the sink. And then, yeah, once you're done, make sure you clean up, flip your burette upside down, and then let it dry. And so you will have this Excel sheet posted on Canvas, and it's pretty simple, but it's going to really help you determine the concentration of our thiosulfates based on the volume of potassium iodide we added, iodate. So, for example, here, this is something we figured out here. This is something we measured in lab. What did it say? 1.8 up to 1.18. Sorry. Let's say it was like 0.18, right? That's something you would have measured in lab. Then the volume of solution prepared, well, let's say 100 mils, but in reality it should be in liters, so 0.1 liters. Volume solution pipetted to Erlenmeyer flask, well, it's 10 mils, right? So same thing, it should be in liters, so 0.001 liters. 1, 2, 3. Sorry, that's wrong. 1, 2, 3.01 liters. And then, of course, all of this is that volume that I was telling you from the burette. You start the burette. You start with an initial volume and a final volume, and so this volume delivered will just be the difference of these two. So if you start with, I don't know, 100 mils, and you have a final volume of 80, that difference will just be 20. So you can do that calculation in Excel. And then you'll do this twice, right? So that's your second trial. Take the average of these two and dump it in here. Average delivered volume, average delivered volume. I don't know why it says to do it twice, actually. This should be just once. Average delivered volume. Oh, right, because it says milliliters versus liters. So you can just convert that. And then your concentration of the potassium solution you made. Remember, that can be calculated based on the moles and the volume. And then the concentration of thiosulfate. Here is where this is kind of the point of the lab, right? This is the whole point of the lab. So this number is what I'm really looking for at the end of this lab. So hopefully you can plug all these numbers in as you're going, and you can start to do some math. But let's talk about it otherwise. So this concentration of iodate is just, remember, moles per liter is molarity. Moles can be calculated from grams that you added and weighed out originally. And then, of course, over, I guess it was 0.1 liters because we were generating this in 100 mils. So you can calculate that to get the concentration. But ultimately, this is where we want to focus our attention because the whole point of this lab was to determine the concentration of this analyte based on our iodate. And so again, it goes back to this formula. And it's funny because I think we've pretty much drilled this formula into you guys at this point of the semester. But this is kind of one application of the many applications that we've applied to. And so here we see if you want to figure out the concentration of this thiosulfate, same idea. Concentration is moles over volume, right? Over liters. And so this is why I say that you need to be meticulous in reading the difference of titrant that you started with, or the amount that you delivered, because when you take the average, that will be your denominator for this formula. And otherwise, here we use the volume of iodate times the concentration, right? Volume times concentration, that sounds a lot like moles, right? And so that's how we get moles there, times our molar ratio, which is here in this case, it's not written out. Well, yes, it is 6 to 1. So times 6. And that, of course, came from that previous formula that I mentioned earlier. Because for every 6 thiosulfates, 1 iodate reacted with it. Or for every 1 iodate, 6 thiosulfates reacted with iodate. So that's why we do a 1 to 6 ratio there. And then just divide those numbers, and that should give you your concentration of thiosulfate. And so yeah, that's pretty much it. It should be a pretty straightforward lab once you get the idea of what we're doing. It's just 2 titrations back to back. We just kind of drip the that's a horrible Erlenmeyer, but 2 titrations back to back, and we just drip our thiosulfate into our iodate until it turns colorless. And then we can just calculate the concentration of the thiosulfate based on how much volume it took to change this iodate to colorless, from purple to colorless. Otherwise, make sure that you take care of all the waste appropriately. And again, just be very, very careful with hydrochloric acid. It's pretty concentrated. So if you get some on yourself, just remember just to rinse it. Don't try to neutralize it, just rinse it with water. But hopefully that shouldn't even be a problem. And that should be it. We will, I guess I'll see you guys in class soon.